This video, we're going to start with a theorem called the integral test. This is theorem 3.4.8 in your book. So here's how this works. This is a test that many of you are probably familiar with that lets you quickly check to see whether a series is summable, is absolutely integrable or not. So let's let f be a function whose domain includes at least the numbers greater than or equal to 1. And then we're going to suppose that f of x, that f is a non-negative function, and that f is decreasing. And notice that implies f is bounded. It's bounded below by 0 and above by f of 1, so we've got a bounded function here. Then the conclusion is that the series, remember series from section 1.4, so the series sum of f of n converges if and only if the f is integrable on the interval from 1 to infinity. That is, this limit integral from 1 to x of f exists. Now, let's start off the proof by saying a little bit about what that convergence means. Now, because f is non-negative, because that means the f of n's that we're adding up are positive, or rather non-negative. So, in particular, all the f of n's are non-negative. So, by a proposition 1.4.6, we have that the series, this converges if and only if the sequence of partial sums is bounded. That is, if you take the supremum over all natural numbers of the partial sum, let's go up to big K so I don't have quite so many things named n. If and only if that supremum is finite. That's just the nature of adding up non-negative terms. You can't oscillate. You're either converging to a number, a finite number, or you're converging to infinity. So when we say converges in this theorem, we mean converges to a finite number. And we can say something similar for the integral too. So remember that our function f is decreasing, it's monotonic. So then by exercise 3.1.4, monotonic functions are Riemann integrable, at least on closed intervals. So in particular, f is Riemann integrable on the interval from 1 to x for any for any number x that's finite, and I suppose let's specify greater than 1, just because f isn't necessarily defined for x less than 1. So that means that this quantity here, the integral from 1 to x of little f, that exists for all little x. Okay, cool. And now let's let big F be the antiderivative. And then you're integrating a non-negative function. So every time you increase x a little bit, you make the antiderivative bigger. So let's prove this formally. If x is less than y, then, and of course they're both in the domain, then big F of y, integral from 1 to y of f, it's equal to this sum, and that's by proposition 3.1.6. And notice this piece is big F of x, and then our leftover piece, integral from x to y of f. This integral here, that is non-negative. This is at least, since little f is non-negative, little f is at least over 0, so this integral is also at least 0, and that is by proposition 3.1.10. So our big F is also monotonic, is an increasing function, and increasing functions have limits. You remember proposition 3.7, any increasing sequence has a limit, and proposition 2.1.8, any increasing function has a limit at every finite point. You can prove an analog to proposition 2.1.8. At infinity, we have that the limit of f of x as x goes to infinity, also known as the limit in the definition of an improper integral, that exists if and only if big F is bounded. So supremum over this interval big F of x, of big F, that supremum has to be finite. So both the summability and the integrability, they're both saying that this integral and this sum, you're adding up non-negative things. So either you go to a finite number or you go to plus infinity, and you're saying that it's equivalent. Either both of them go to a finite number or both of them go to infinity. Okay, so that's what we're trying to prove. So now we're going to define some functions whose integral has sort of a handy property. So here are our coordinate axes. Here's the graph of, let's say, y equals f of x. And then I'm going to go ahead and put a dot at every integer. And now let's say I wanted a function whose integral was the sum. So here is how we're going to define our function g of x. It's going to be this function. It's constant on each of these little intervals. And then if you look at this carefully, you can see that the integral of g is the same as the sum of fn's. So we'll write that out precisely. So we define g of n to be equal to f of n if n is a natural number, and then g of n plus x is going to be f of n if n is a natural number and x is in this open interval from 0 to 1. And you can write any real number like this. You can write any real number as an integer plus a real number between 0 and 1. If you're talking about a number bigger than 1, which we are, you can write it as a natural number that is a positive integer plus a number between 0 and 1. And then because f is decreasing, we have that g of x, actually, why don't I call that g of z is greater than or equal to f of z for all z greater than or equal to 1. Z is an n plus x for some natural number n and x in our unit interval. And then g of z is f of n is greater than or equal to f of n plus x, also known as g of n plus x. So therefore g is bigger than f because f is decreasing. We're going to need a similar function that's not bigger than f, that's less than f. So we'll draw that exactly the same way, only extending it the other way. It's called that h. So g and f and h, they're all the same thing at the integers. At the non-integers, g matches up with the previous value of f, h does not. H matches up with the next value of f. And then arguing exactly as before, we see that f of z is bigger than or equal to h of z for all z bigger than or equal to 1. So now let's write some sums as integrals. So we're going to notice g of x equals f of n if n is an integer and less than or equal to z is less than n plus 1. So f of n is the same as the integral from n to n plus 1 of g. And thus, a partial sum from n equals 1 to, say, k, f of n elementary induction argument that turns into the integral from 1 to k plus 1 of g. Then very similar argument. Our partial sum of f of n. That's the integral from 1 to k of h, and then you have to add h of 1 or f of 1 to it, because h doesn't take on the value f of 1 between 1 and infinity, well, only at one point, so you just have to add that one on. You can't get it from integration. So now I think we're ready to write out this proof. So let's suppose that our sum converges. And then, as we said before, by proposition 1.4.6, we have that supremum, the supremum of the partial sums that is finite. So we have that the supremum of these integrals is finite. And now and then we are going to pick some real number x in this interval from 1 to infinity, and let's let k be a natural number with k bigger than x. By the Archimedean property, k has to exist. Then because our function big F is increasing, and remember that's by proposition 3.1.6 and 3.1.10, and because little f is monotonic, if you integrate up to f, that's less than or equal to integrating up to k plus 1, and then that's less than or equal to the integral from of g, and that's by proposition 3.1.10. And so the integral from 1 to x of f, that's less than or equal than the sum from n equals 1 to k f of n. We saw before her that is precisely equal to this integral of g. And then again, this is again by proposition 3.1.10. This is bounded below by 0. So we have that supremum of these integrals that's less than or equal to the sum of fn. That's less than or equal to the sum of fn, or rather it's less than or equal to the supremum of the g of n's, the supremum of these partial sums, which we saw before was finite. So our integral converges. Converse is pretty straightforward, so let's suppose that our integral converges. Then we work in reverse. The supremum integral of these partial integrals that supremum is finite. So, but if you take only the integral, if you look only at k an integer, you're taking the supremum of fewer things. If you look only at if you look only at the integers, you're looking at fewer values than if you look at all possible real numbers in this range. So the supremum can't be any bigger, so that's finite. But integral from 1 to k of h is less than or equal to the integral from 1 to k of f and that is usual, and that we said before was proposition 3.1.10, and because h is less than f, so we've got, so sum from n equals 1 to k f of n, that's f of 1 plus the integral from 1 to k of h, less than or equal to integral from 1 to k of f, less than or equal to the supremum that's finite, and then we put a supremum. Then we just take the supremum of the left-hand side, and then the right-hand supremum, that is an upper bound, a uniform upper bound on this set. The sum from n equals 1 to k is less than or equal to the supremum of those integrals no matter what k is. So we have that the series converges by proposition 1.4.6. The integral test that we've just proven, it's often used to go from an integral that you know converges and a function that you know is absolutely integrable from 1 to infinity, and from there get a function, get a series that is summable, or a series that converges absolutely. Since we're talking about non-negative things, convergence is the same as convergence absolutely. But sometimes it's convenient to go in the other direction. Sometimes you want to go from a series that converges to an integral that you'd like to show converges. All right. Also, everything we've said has been for non-negative functions. Absolute convergence of series gives you absolute convergence, absolute integrability of a function since everything's non-negative. So I'd like to finish up this video by proving sort of a similar theorem, one that we could use for conditionally convergent series. This isn't in the book, but I think it is useful for the example we're going to ask you to work out on your homework. So here's the theorem. Let's let f be a function with, let's say, the same domain as before. And then we're going to say, we're going to suppose that f is locally integrable. So you can't have f being like the characteristic function of the rationals. It can't be one of these functions that doesn't have a Riemann integral even on closed bounded intervals. And we are also going to suppose that the limit as x goes to infinity, f of x, we're going to suppose that that limit is 0. And the conclusion is that f is integrable, improperly integrable, that is integrable on this unbounded interval. That's true if and only if this sum converges, possibly not absolutely, but at least conditionally. Now, with conditionally convergent sequences, you have to be a lot more careful than with absolutely convergent sequences, which is why this isn't a theorem about convergence of f of n. It's a theorem about convergence of little integrals. So this you would generally use if you can show that the series converges to show that the integral converges. As an example of why we need this limit is x goes to infinity, f of x condition. So as an example, let's let f of x be the sine of 2 pi x. Then integral from n to n plus 1 f, that's the integral from n to n plus 1 sine 2 pi x dx. And if you evaluate this antiderivative, you all remember Cal 1 well enough to do that, you end up with a 0. So, of course, our sum converges. Since it is equal to the sum from n equals 1 to infinity of 0. All the partial sums are 0. But then the integral from 1 to x of sine n pi x. Sorry, 2 pi, we need a different variable, t dt. That is equal to cosine of 2 pi x to 1 minus cosine 2 pi x all over 2 pi, which oscillates. That is the limit That's the limit of this quantity. Does not exist. So f is not integrable. On this interval. There are other possible conditions you can impose. There are functions whose limit is not 0 but nevertheless converge. But this limit as x goes to infinity f of x, that is a condition that will at least work for us. So let's prove this theorem. So let's start with the forward direction. Let's suppose f is integrable on our interval. And what does that mean? That means the limit as x goes to infinity, integral from 1 to x f exists, or there is a real number L such that the limit is equal to x to L. And what does that mean? That let's write out the epsilon p definition of limit at infinity. So for all epsilon greater than 0, there is a real number p such that if x is bigger than p, then this integral from 1 to x of f minus L is less than epsilon. All right, then we're just going to pick a integer or a natural number that's at least p, and then by the Archimedean property, there is at least one, so k exists. And then if n is a natural number and n is at least k, then we've got that the integral from 1 to n of f minus L is also less than epsilon. So basically we're saying that the limit is L if we look just at integers. And then by proposition 3.1.6, integral from 1 to n of f, that's the sum from, what letter have I not used yet? J equals 1 to n minus 1, integral from j to j plus 1, f. So we have that. So we've seen that the partial sums are converging to L. That converges to L by proposition 1.3.3a. That's all the way back at the start of the semester convergence of sequences. So we've got that the infinite sum that converges, and in fact it converges to the same thing. You don't get the same limit in the theorem we proved early. You're the one about absolute convergence, the one about sum being f of n rather than the integrals of f, but in this case you in fact do get the same limit. Now let's prove the reverse direction. This is the direction where we're going to use the fact that f goes to 0 as x goes to infinity. You'll notice we didn't prove that. The other direction is true whether f converges to 0 or not. So we're going to suppose that our sum, that this thing converges. And that means, let's let L be the name of the thing it converges to. Usual notation, L is the sum from n equals 1 to infinity of whatever it is you're adding up. And then convergence means for all epsilon, there is, for all, positive epsilon, there is a natural number n such that if, let's say, little k is bigger than n, then sum from n equals 1 to k of that integral that is within epsilon of L. And then we use proposition in 3.1.6 again to turn this sum of integrals into one big integral. Actually, I think I don't want an epsilon here. I'm going to say we would like an epsilon over 2. And then by proposition 3.1.6, if k is bigger than 1n, then we have that integral from 1 to k plus 1 of f minus L, that's less than epsilon over 2. All right. Now, we'd like to show that this integral converges to L as the upper limit k plus 1 goes to infinity, but we don't want to look just at integers. We want to look at all real numbers. And if something's true for all real numbers, then it's true for all the integers, but the reverse is not true. There are plenty of things that are true for integers, but not for all real numbers, so we're going to have to do a little bit more work to allow us to have an upper limit that's an arbitrary real number. So since the limit of f of x is 0, there is a real number p such that if x is bigger than p, then f of x in absolute value is less than epsilon over 2. We are going to let let's call it capital M. We haven't used that letter yet. Capital M is going to be a natural number with capital M. It has to be bigger than, we'll see why in a minute, both big N plus 1 and big P plus 1. By the Archimedean property, big M exists. Now, let's suppose X is a real number and that X is bigger than big M. Then we're going to let K be the natural number that satisfies K plus 1. X is between K plus 1 and K plus 2. X is bigger than M. M is bigger than N plus 1. N is a natural number, so it's at least 1. So M is bigger than 2. M is bigger than 2. M is at least 3. So X is at least 3. K plus 1 is at least 3. K is at least 2. K is a natural number. And then this thing, the integral from 1 to x of f. We're trying to show that has a limit, and that limit is L. That is the integral from 1 to k plus 1 of f plus the limit from k plus 1 to x of f. So let's take some absolute values. Absolute value of the integral from 1 to x of f of L by the triangle inequality. That's the integral from 1 to k plus 1 f minus L plus the next piece, integral from k plus 1 to x of f. Now, let's think for a minute about what we can say about k. So we've got that k plus 2 is bigger than x. So we have that k plus 1 is bigger than x minus 1, which is bigger than m, which is bigger than, sorry, because it's x minus 1, this is bigger than m minus 1, which in turn is bigger than p. So if y is bigger than k plus 1, then y is bigger than p, and so in particular f of y is less than epsilon over 2. So that second piece, integral from k plus 1 to x of f, that's less than epsilon over 2 times x minus k plus 1. And then k plus 1 is the biggest integer less than x, so this can't be any bigger than epsilon over 2. X minus k plus 1 is always, in fact, strictly less than 1. All right. Now, also, we have that k is bigger than x minus 2 is bigger than m. M and n are integers, so if m is bigger than n plus 1, m is bigger than n or equal to n plus 2, and then we subtract 2. I forgot to subtract 2 from the m, sorry. So k is bigger than n. So this first part, integral from 1 to k plus 1 of f minus L, that's also less than epsilon over 2. So if x is bigger than our big M, then this integral is within epsilon of our limit L. So the limit as x goes to infinity, integral from 1 to x f is equal to L and exists. And that completes the proof.